Alrighty, in this video we are going to be talking about particle motion in terms of polar equations. Um, Essentially, the goal of this is to understand what each derivative is saying, because you have these 8 derivatives that you are expected to memorize and understand and know what they mean, and I think it's going to help you guys if you visually see what each thing is saying. Now, here's the thing about dxdt and dydt. Um, this is essentially like your basic PVA problem where you're moving to the right, or you're moving to the left, or you're moving up, you're moving down. So remember that dxdt is going to be the rate of change of your x coordinate with respect to time. So are you moving to the right, or are you moving to the left in terms of your particle? Same thing with dy dt. Are you moving up or are you moving down? In this case, we don't need to reference the radius because we're only looking at the x component, y component. So anytime you have dx dt, dy dt, it's either the x component or y component. Just your basic PVA. Now, if you're given something like drdt, though, this is talking about the rate of change of the radius with respect to time. So this is essentially saying, is your radius getting bigger or is your radius getting smaller? If it's getting bigger, then this tells me that the particle is moving away from the origin because the radius is obviously going to increase. It's getting bigger. Or the particle is moving towards the origin, aka the radius is decreasing or getting smaller. So then you would say it's moving away from the origin at time t is equal to 1 because r prime of 1 is greater than 0, the radius is getting bigger, or r prime of 2 is less than 0 because the radius is getting smaller. You'll most likely need to use the chain rule unless they give you the derivative with respect to t already, but most likely they won't, so you'll just have to do dr d theta times d theta dt, which is part of 2025 BC2 Part D. So I'm not going to do all of this. We'll probably do it in class together, but so we had this little thing right here. So we had r of theta is equal to 2 sine squared theta. So notice how this was not given in terms of t, right? But in part D, it told us that d theta dt is equal to 15, and we want to see the rates at which the particle's distance. So anytime we're thinking about distance, we're thinking about the radius of that particle. So is the radius of that particle increasing, or is that radius of the particle decreasing? If it's increasing, it's moving away. If it's decreasing, it's moving towards the pole, or moving towards the origin. So in this case, we had dr d theta times d theta dt. You know that d theta dt in this case they gave us was 15. So 15 times dr d theta, which you could have found because they gave you r theta in terms of the original problem. Like I said, we're not going to go deep into this, but that's what that means there. And then, because this is 15.465, this tells me that we are moving away from the origin, so the radius is getting bigger. All right. Your notation is going to be very important in terms of your interpretation. So in this case, the particle is moving to the right at t is equal to 1 because x prime of t is greater than 0. Well, notice how we have x prime of t. Explicitly give me that t is 1 right here, so you would say x prime of 1 is greater than 0. The particle is moving to the left because x prime of t is less than 0. No, because you want to give me a time. There. Then, of course, just pay careful attention to linkage errors. Unit 4 is very bad in terms of your linkage errors. So please make sure that you're doing it by line and writing it separately in terms of your justifications. Alright, so we went over dxdt, dydt, and drdt, so all of these were with respect to time. They were easy peasy lemon squeezy. It's either moving to the right, moving to the left, or the radius is getting smaller, or the radius is getting bigger. So the particle is moving away from the origin or close to the origin, towards the origin. Now, whenever we are talking about the radius here in terms of theta, so in this case drd theta, if the signs are different, we're just moving towards the pole, and if the signs are the same, then we're moving away from the pole. Essentially, it's the same thing with PV in terms of speed, right? So remember how back in AB we said that, hey, if we had the same velocity and acceleration, that we were moving away. But if we had different velocity and acceleration, we were moving towards the origin, or towards zero, or towards whatever. So in this case, it's the same thing. So if the signs are different, then we're moving towards the pole, aka the origin. If the signs are the same, we're moving away from the pole. So I have a Desmos right here where we have this lovely polar function right here. And I want you to look at the original, so R of A, and then I want you to look at the derivative and see what happens in terms of the radius as I am moving it. So for example, here, notice how R of A and R prime of A are both positive, so your radius is moving away from the pole, away from the origin. But then after pi over 2 or so, we're getting closer to the origin, because notice how R of A and R prime of A have different signs. So that's in terms of drd theta. Now, likewise, this also applies to dxt theta. Whenever we are thinking about dxt theta, we're thinking, okay, are you moving towards the y-axis, or are you moving away from the y-axis? Essentially, this is saying, is your x component getting bigger, or is your x component getting smaller? But instead of us saying the x component, we are talking about the y-axis. So whenever we're thinking about dxt theta, once again, let's say that I have this function where I have r cosine of theta, and then if I were to look at my derivative and my function value, notice how, because my values are the same signs, that we are essentially moving away from the y-axis. But then once we hit a sign change here, notice how we're getting closer to the y-axis now. So this is essentially saying that the x component of the particle is getting closer to 0. And then same signs, negative, negative, we're moving away from the y-axis, which means that my x components of the particle is moving to the right. And then, of course, same thing with dy d theta. So whenever you do r sine of theta here, you're moving towards the x-axis, or you're moving away from the x-axis. So in this case, it's like your y values are increasing or your y values are decreasing. So same thing here. Notice how my y values are increasing here. They're going up, 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 meaning that my particle is moving away from the x-axis because I have the same signs. If I have different signs here, notice how now I'm moving closer to the I'm moving closer to the x-axis, or my y component is decreasing and moving towards the origin. So you just really need to think about what's happening in terms of, are you given dy d theta? If you are, then what's happening to your y value in terms of theta? And then that just talks about the moving towards or away the x-axis. For dx theta, think about, okay, what's happening to that? And then think about, is your x component moving to the left, moving to the right? Is it moving towards the y-axis? Is it moving away from the y-axis based off of that? And then, of course, same thing with dr d theta here. So, for example, here in part C, where they give you dx theta, and it says find the value of theta that corresponds to the point on the curve C that is farthest away from the y-axis. Notice how one thing that should click with you is that they gave you dx theta. Since they gave you dx theta, you know that it has to do something with the y-axis. Now, because it says farthest from the y-axis, this tells me that my x component is going to be at its maximum value. So in this case, if I were to look at this here, and I did r cosine of theta, this is what I have. And I want to look at the maximum x coordinate, which is like, I can't really click on it, but like right here in terms of your max x coordinate. Now, of course, you could probably put this in rectangular mode. So 2 sine square of x times cosine of x to get your rectangular mode in terms of x being 0.955, or in this case theta being 0.955. So this is saying that when theta is 0.955, then we're going to get an x component of whatever this is right here. Now, of course, on part C, they gave you the derivative, so you want to use the derivative, set that equal to 0, find your critical points, and then plug in using r cosine theta and call it a day. Alright, so hopefully this video will help you guys visualize in terms of what the particle is doing, because who knows if we'll get another polar FRQ.